what we're going to do is we're going to take a look at the sums of radicals. Now, if I say a sum, I also by default imply difference, because difference is defined as adding the opposite. Thank you. So a difference is indeed actually a sum. Now, here's my rule of thumb. Treat these like variables. Therefore, simplify whenever you can. Combine like variables the same way that you would combine like terms. So simplify and then combine like variables, just like terms. For example, please take a look. 2 root 5 plus 8 root 5. How many root 5s is it, everybody? Treat it like variables. Yeah, it's just 10 root 5. Well, where's the variable? What am I talking about? Think about it this way. What would you get from 2x plus 8x? 10x, right? So that's what I'm referring to. It's analogous. The way you treat them is analogous to variables. So how about multiplication? Same thing. If I were to multiply things, wouldn't I multiply 2 times 8 to give me 16? And wouldn't I do x times x to give me x squared? So the same thing occurs here. Had this been multiplication instead, it would be 2 times 8 on the outside and 5 times 5 on the inside. Just like variables, you would treat them. You multiply coefficients and multiply x and multiply variables. So wherever you see a radical term, think of a variable. That will help you if you're having trouble with combining like terms. In this case, combining like radicals. Let's get on to this then. So 48, 75, are those like radicals? Are they?
Yeah. No.
Are they the same numbers? The question, Max. Clearly not, right? So Max, can you make them into like variables?
Yeah.
All right, so tell me, what should I do with 48, Max? 4 times? Yeah, so Max is breaking that up into root 16 times root 3, which is 4 root 3. Somebody else for 75. What does 75 break into? Use your context clues. If a root 3 is left over here, there's probably a root 3 here also. There's probably a root 3 here also. What goes into 75? What do you got, Hannah?
25 and 3.
Yeah. Root 25 and root 3, which is 5 root 3. Well, I've got 4 root 3. I've got 5 root 3. So, George, what do I have all together?
You have 60.
I've got 4 apples
Oh, yeah.
and 5 apples. How many apples do I have?
You have 9 root 3.
Yep. Remember, George, when you're in doubt, treat the radical like a variable. So if you had 4x plus 5x, it would be 9x. See what I'm saying by that? Okay, treat the radical like it's a variable when you're combining terms. It might help you to remember your, I don't want to say rules, it's not really a rule, but you remember the understanding of how this process works. How about part B? Are those like radicals, 3rd root 16, 3rd root 54? No, obviously. Give me perfect cubes that work for this, please. Part B, I know the 5 remains there. What do I break the 16 into? The 16? Just tell me what to break the 16 into, though, first.
8 times 2.
8 times. Yeah, is that what you said? Sorry, I thought you said 10. So the cube root of 8 becomes 2, which is what gives you 10. Okay, so the cube root of 8, the 3rd root of 8 is 2. So that's the process of the first part. Now, use your context clues. If you have the 3rd root of 2 left over in the beginning, what do you think you're going to have with the other one? Come on. The cube root of 2 also. You'll most likely have that, because that's the only way you'll be able to combine like terms here, right? So there's a good chance that you're going to take a 2 out of 54. If you take a 2 out of 54, what's left over? 27. Isn't that a perfect cube? It's not a coincidence, okay? So a perfect cube of 27, or cube root of 27 times cube root of 2. Cube root 27 is really just the 3 times cube root 2. So I've got 10 cube root 2 minus 3 cube root 2 Annette, what is my answer?
Where are you? I was taking notes.
That's all right. We're at 10 cube root 2 minus 3 cube root 2. Where's my final answer from this? What does it become?
7 cube root 2.
Yeah. We just treat this like variables. Okay, if I had 10x minus 3x, it would be 7x. How about part C? This is kind of a tricky one. It's not terrible, but it's a little bit tricky. 50 thirds plus 2 thirds. See what I did already? That's the first step I would take for a problem like this. I took the fractional radicand and I wrote it as the square root of something over the square root of something. I broke up the square root on purpose. Why might I have done that? What does that illustrate to me now? When I combine fractions, what do I always need? When you add fractions, you need a, come on, thank you. Do you have one?
Yes.
You do. You absolutely do. So the numerator you can think of as just 50 plus root 2. Sorry, root 50 plus root 2. And the denominator is simply root 3. Why might that help me? What's 50 really? What does 50 really break up into? Yeah, 50 is really root 25 and root 2. A lot of you are jumping right to the answer. That's totally fine. You don't have to show me the 25 and 2. Okay, so if you see that 50 is simply 5 root 2, just jump right to that on the next line. Again, 25 becomes a 5. The root 2 carries down, which gives me 6 root 2 over 3. Follow the arrows. Am I done? 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 What do you have to do? What's the last step for these? Oh, sorry. First of all, there's a radical there. What's the last step for these problems? What's the last step we have to consider?
You just multiply by root 3.
Why root 3 over root 3, Annette?
So you can just, you don't want a radical in the denominator.
Yeah, you want to get rid of the radical in the denominator, so you multiply by itself over itself. Max?
Where'd you get the 6 from?
5 plus 1. There's really a 1. It's tough to see, but there's a 1 in front of here, really. See the 1 right here?
I see.
5x plus 1x. Okay? Yeah, think of that with a 1 in front, because a 1 is always in front of everything. So root 3 by root 3 gives me root 9, which is back to 3 in the denominator. The numerator becomes 6 root 6. Now, please be careful here. Only things on the outside can cancel with things on the outside, meaning on the outside of the radical. So that radical 6 in there, you can't touch it. Remember, it's like having 6x. Remember we kept saying x? Think of this root 2 here as x earlier. Still think of this as 6x over 3. If you had 6x over 3, the 6 and the 3 reduce, but the x wouldn't. So this simply becomes 2, and this becomes a 1. So your answer is 2 radical 6. Okay, the last step is the one that I see a lot of mistakes on. Students try to reduce the radical that's underneath with the 3 on the outside. You can't do that. Okay, again, the 3 is on the outside, the radical 6, the radical portion is on the inside. Questions on this process? Okay, so now let's get to the tougher stuff. There's only 2 examples, I think, in these whole notes today, really. I think it's just, this is the second one, yeah. Okay, so this is the last thing we want to do here. But it's a lot lengthier than the last one was, right? Try part A on your own. Think about what you have to do. Give me so much time. 11, 12, perfect. Still have about 8 minutes. Try part A, see what you think you would do. If you hit a roadblock, maybe ask the person next to you how to help. Look for a little bit of help. B and C are really tough. If you get A, feel free to move on to B and C. Oops. I'm going to put the negative. I should really distribute, right? If you want to check up, you can feel free to look up to see that you're on the right track at least. Okay, you don't have to look at all the work, but look at the first line at least still. Remember, whenever possible, break things down. If you finished A, check your answer, please. If you finished A, check your answer that it's right, please. And just keep breaking things down more and more. And distribute the negative, please. At first, I made a mistake with the positive. But in the line, when you drop the parentheses, the negative goes to here, and this negative becomes a positive. I know some are on B already. Keep working. Questions on A. For those still looking at A or working on A right now, please ask me any questions.
I did B, I just don't understand this.
Okay, so let me point you through, okay? So I look up here first, and I see that I can break down 48. That makes sense, right? And then this makes sense? Because the square root of 16 is? And then what's 5 times 4? So is this good over here?
So you still apply that part.
Make sense? All right, now over here, when I multiply, if you're confused at all, maybe look up right now because this might help. I multiply the outsides, 4 times 3, and then I multiply the insides, 6 times 2. Because remember, it's like a variable. If this was 4x times 3y, it would be 12xy, right? So 4 times 3 gives me 12, 6 times 2 gives me 12. Now I take this same number here, this coefficient, 4 root 6, and distribute it here also. So I do 4 times 5 to give me 20. And then I do 6 times 3 to give me 18. Then after that, I have to go through the breaking down process. 12 is really 4 times 3. 4 is really 2 when square rooted. 12 times 2 is 24, and keep carrying down. Over here, 18 breaks up into 9 and 2. 9 is really 3 as a radical. 3 times 20 is 60, and that carries down. Well, this is negative. I have negative for this one. This is negative, negative, which makes that a positive. So then when I get this minus this, I got 20 root 3's minus 24 root 3's give me negative 4 root 3's. Does this combine? No, because these are not the same radicand. It's like saying negative 4x plus 60y. You can't combine those two things. Okay? Let's look at part B. For those that are already done, I'll start putting up the work for B. 4x, we got x cubed, x, all right. Okay. So in this problem, we have to consider the fact that we have to take out only parts of the x's. So this is part B now. So I would go like this to start. I would say to myself, well, this I could take out, but this I can't. So I always break it into a perfect square and a not perfect square. Then the right part, I would break it into x to the fourth and x. Now, as I go through this process, I'm going to see that, yeah, although this is absolute value x, it's still going to work out. So look at the process taking. The square root of x squared is just absolute value x. The square root of x to the fourth is x squared, right? 4 divided by 2. Take the power over the index. Now, that's absolute value x. It's got to be a positive number. Multiplied by x again. We're multiplying with 2, so even though it's not mathematically perfectly sound, we can say this. So really, this is like saying I've got 4 x squared root x minus 1 x squared root x. So now, your coefficients in this case are really the 4 and the 1. and think of this as your variable. Think of this as your variable. Again, this is like 4 of these things minus 1 of these things. So it's 3 of those things. So it's 3 of these x squareds root x's. Okay, this is the step that's a little bit shady, because absolute value of x means this has to be positive, right? And theoretically, if x were negative, it'd be negative times positive, which would be negative, so that's not true. So the statement in the beginning of the problem really should say that x is greater than 0. That's a domain restriction. The problems in your text tell you ahead of time, make sure all the variables represent positive numbers. That's how they start these problems. Okay.
Could you just, in the beginning, distribute that x back in and make it
Yeah.
square root of x to the fifth to make it easier, and then just do
Get 3.
You do 4 to the x to the fifth minus x to the fifth, and then it's just 3x to the fifth, and then you just multiply it, and it's a lot.
Kate makes a lot of sense. So let's take a look at this with another approach. How does this come out? Take a look at what I'm pointing to, please. How does this x come out? If you had an x squared under the radical, it would come out, right? Like, look, this x squared, it became an x. So this, if you want to put it back in, you could put this back in as an x squared term. Again, think about that. Where would you get an x on the outside if you took the square root of x squared? So moving this on the inside, it makes this really the same thing as doing this. So Kate is saying, up this degree of 3 by 2, because you move this in as x squared, so it becomes this statement, which then makes it a little easier to do it like this, right? 4 root 4 times the square root of x to the fifth minus 1 times the square root of x to the fifth. And then as a result, you get 3 of those, and then Kate is saying, well, just do this now. And this becomes this. Again, giving you the same answer. I agree, Kate. Good, really good. Good job. Good intuition. Okay, it's a much shorter option. When you see those alternative roots, take them. That's fine. Okay? Make things easier for you. Make life easier. But in the end, you get the same answer. Either way. For the sake of time, I want to quickly go through C. It's a little bit tricky. C is 2 times the cube root of y to the fourth over 3 plus 5 times the cube root of the fraction 2y to the fourth over 54. Okay, this 5 is like a coefficient right here. This 2 and 3 are like 2/3 as a coefficient. Now, when I start a problem like this, the first thing I think about to myself, oops, I copied it wrong. Did I copy it wrong? No. So put a 4 here, sorry. The first thing I think to myself is, can I break something down? And sure, in this problem I can. I can break up my y to the fourth. What would I break it up into?
Y squared plus y squared.
Y not squared.
Y cubed. Y.
And y. Because I'm looking at a perfect cube now, right? And on the right side, I break this one up. I've got a 5. The numerator, make it cube root of y cubed times the cube root of, well, the 2 I'll talk about in a second, times the cube root of y again. Now, recognize here, please, look, 2 and 54. What's 2 divided by 54 reduced to? 1 over. 1 over 27. So cancel here, put a 1. Cancel here, put a 27. It makes life a lot easier for me. I'm going to run out of time there. But you're going to see the bottom become a 3 here. You'll see the numerator become 5y cube root y. Over here, 2y cube root y. They're both over 3. You have a common denominator. Just combine. You'll get 7y cube root y over 3. Okay, combine the numerators. Practice tonight, please. Make sure you practice.